Okay, for week 3, we're going to talk about confidence intervals. All right, so really before we get into some confidence intervals, one thing we want to assume for our course that everything, again, is around the normal distribution. So if we draw a bell curve, as our normal distribution, again, Z is a very special normal distribution where the mean is 0 and the standard deviation is 1. We talked last week, this is the tables, right? Well, this is kind of important with confidence intervals here. So if this is a standard normal, that means its mean is 0, which is centered at 0, and it deviates by 1. So 1 standard deviation away to the right, 1 standard deviation away to the left. I'll put a little minus sign in front of it. A plus here so we know we're going to the right. 2 standard deviations, plus, not really drawing the scale. Right? And we know, based on the empirical rule, that's approximately 95% of the data. So, the way... Sorry about the phone. All right. So, back to where we were. So, we're on the normal distribution, empirical rule 2 standard deviations away. Now, with confidence intervals, you're actually going to be able to calculate exactly how far away you are. So, the empirical rule is a good tool, but now we're going to learn how to do it. And we're going to do 3 different types of confidence intervals. So, the first thing before we get into confidence intervals is we need a point estimate. Right, so we will build 3 types of confidence interval. We'll do one for the proportion p. We will do two actually, for the mean mu. So a good point estimate for p is p hat. Remember, how do we find p hat? P hat is success over n. Whatever our event is, divided by how many samples we have. That is p hat. That is a sample. A point estimate is a sample statistic. Mu, point estimate, is x bar. Well, how do we find x bar? Well, that is the mean. Add up all the data points, divide by how many you have. So, how does this help us? Well, let's kind of understand what we're doing here with a confidence interval. So, when we do confidence intervals, we want to say how confident we are that the true population parameter, either p or mu, lie within a certain interval. Right? So, a common confidence interval is 95%. Right? So, if we do a 95% confidence interval, and we always do 2 tails, not always, but in this course we always do 2 tails, we know that's approximately, no, wrong place. That's approximately 2 standard deviations away. So what we know is that inside here, we want it to be 95%. Well then, what does that mean? Well, we have this area out here in the tails, right? And this is known as alpha. So how do we find alpha? Alpha is this little symbol like this, and that equals 1 minus your confidence interval percentage. So in this case, if we're doing a 95% confidence interval, alpha equals 5%. All right. So let's move our point estimates here so we have a little more room to work. Well, if alpha is 5% and we have 2 tails, well, that means this area in this tail is alpha over 2, and the area in this tail is alpha over 2. Because if I combine these 2 tails, I have alpha again. So therefore, I have 0.025% in this tail and 0.025%, not percent. Get rid of that. I combined my decimals and percentages, sorry about that. So I have 2.5% in this tail and 2.5% in this tail. Remember, if you want to give it a percent sign, you move the decimal 2 places. So basically, all confidence intervals come down to a formula, and they're going to look ugly. I'll go to a new page and draw this a little bit smaller. So you have a normal distribution, because like I said, the confidence intervals we are doing are always a thing. Whatever our confidence interval percentage is always in here, and this is always alpha over 2, alpha, that's ugly alpha, alpha over 2. Now, you want to take your point, whatever population parameter you're solving for, so either it's going to be a p or a mu in our case, and basically you are going to add and subtract some error. You're going to add and subtract some error, right? And the error is these ugly formulas that everybody doesn't like. But if we kind of think about it logically, it's not too bad. So let's apply kind of a formula we've already seen before. We'll get rid of this guy here for a minute. Remember, if we stick with this guy being a z, which means he's centered at 0, I know that this whole thing is z, and the probability is always equal to 1, right? Because probabilities go from 0 to 1. So if I cover every possible option inside under the curve, it has to equal 1. So therefore, if this is a z, that means this is the limit z alpha over 2, and this is the, well, negative because we went to the left, and this is z alpha over 2. We already talked about what alpha over 2 is. Z, and so what these two things are our critical values. All right, and that is a very important terminology we'll use for the good remainder of the course. Those are the critical values, are the boundaries. It is where my confidence interval stops, my confidence interval percentage stops, and my alpha starts, right? And the tails, typically we want to look at this as the bad region. When we get into next week, we'll talk about hypothesis testing and rejection. Well, we want to reject if we ever fall into this bad region. For now, what we're going to build is confidence intervals, and we're going to find these limits. We're going to figure out what this value and this value is. Well, for a standard normal, that's not so bad because we're always centered at 0, right? But and typically, not all problems are that way. So we're going to have to deal with real-world problems, so we have to convert things. But before we get into that, we know, like I said, we're going to have the limit. I'm going to probably go to a new page, and I'll come back if I have to. We got the lower limit, which is negative z alpha over 2. And then we have the upper limit, which is z alpha over 2. And somewhere in the middle is the true z, or our confidence interval percentage, right? Well, we learned a formula for this last week for what z equals. So if I replace, we'll leave this guy like it is for now, less than equal, z equals what? Z equals x bar minus mu all over sigma divided by the square root of n. Right? Now, if we do a little bit of algebra, we can get rid of this guy by multiplying it by itself. And again, that would be negative z alpha over 2 sigma over the square root of n less than equal to x bar minus mu greater than z alpha over 2 sigma over square root of n. Now, if I subtract an x bar from each side, I get an x bar minus z alpha over 2 sigma over the square root of n. I'm going to run out of room. Less than equal to a negative mu, less than equal to negative x bar plus Z alpha, all of this. Running out of room. I gotta write smaller on my iPad, I guess. On the next page, see if I can write this a little bit better. Negative x bar minus Z alpha over 2 sigma over the square root of n is less than equal to a negative mu is less than equal to negative x bar plus Z alpha over 2. No, can't still write smaller. If I multiply this whole thing by negative 1 to get rid of this negative guy, that's going to flip all my signs, change all the signs. Basically, it just swaps everything. So what I end up getting is still x bar minus Z alpha over 2, it's an alpha, sigma over the square root of n, less than equal to mu, less than equal x bar plus Z alpha over 2 sigma over the square root of n. So here is my population parameter mu. Here are my point estimates, which we just talked about. And then this part is the same on both sides. The only difference is the plus and minus. This is my margin of error we just talked about a minute ago, where I said you take some point estimate and you add and subtract the e, and that will give you your limits of your population parameter mu. That's the concept between confidence intervals, and probably more than you really need for this. But it kind of helps you understand what's going on. So when you're applying the formulas, you can see what you're doing. All you're doing is, when you're doing confidence intervals, you got to read the problem and figure out what population parameter you are solving for, right? So first, what's your parameter? And in our case, you only have really two choices. You have P and mu. Well, P, if you're doing anything that has to do with percentages or proportions in the problem. And mu is anything that's dealing with the mean. There are other confidence intervals. There is confidence intervals of sigma squared, variance, and its point estimate is S, which we just learned how to do, S squared, which is standard deviation and variance. So, first thing when you read a problem, and again, these are the two that we're going to be doing in this course. What parameter? Is it a proportion problem or is it a mean problem? Then, once you know that, step 2, find point estimate. So P is approximately P hat, mu is approximately X bar. Then find margin of error, big O-D. And in the announcement, I posted the formulas for finding margin of error because it changes every once in a while. They're a little bit different, but that is basically the concept of confidence intervals. Now, it wouldn't be statistics if there wasn't one possible loophole. So, the good news is anytime that we're dealing with P, we always use the standard normal Z. All right, and we learn how to calculate all that in week 2, and we'll learn how to calculate our critical values. Remember, our critical value is Z alpha over 2. The issue is mu. Mu has choices. Mu can be either Z alpha over 2, a standard normal, or we're going to learn a new critical value, T. Let me get capitalized because it's a distribution. T alpha over 2. Concepts are still the same. We'll get to that here in a second. There's not a big difference between just two different distributions, a Z or T. How do you know which one to use? You use the Z when you know sigma. What is sigma again? It's the population standard deviation. There'll be problems where they tell you know this. In real life, though, typically you don't know sigma. Because if you know sigma, then you probably know the mean, right? Because if you go back to last week, how to find standard deviation, to find standard deviation, you have to find variance. Well, how do you find variance? Well, it is how dispersed you are from the mean. So how can you find out how far away from you are from the mean if you don't know the mean? So that's why typically with this case is never used. Instead, we use this to t when we unknown sigma, so we use S, the sample standard deviation, which is what we calculated last week. So if you're comfortable with finding sample standard deviation, you're good. If you're not, we definitely need to keep working on that, and I would highly encourage you to use technology because calculating the sample standard deviation by hand is very tedious. So let's talk about the Z or T to finish out this video. So we have our bell curve, standard normal, that's centered at 0. That is the Z, 0, 1. Mean of 0, standard deviation of 1. The T distribution, I'll draw it in red, it looks very similar, right? Except for instead of knowing anything, well, it's still centered at 0. They're both centered at 0. They're both bell-shaped. The difference is, not really drawn real well, but the difference is it's a little wider in the tails. This allows for a little more error, right? And so with a T, you know it's centered at 0, but you don't know its standard deviation. Instead, we use this thing df, which is like a little funky v, which means degrees of freedom. And the little funky v equals n minus 1. So you just take your sample size and you subtract 1. Again, this is the T and this is the Z. They look identical. The only difference is the T's a little fatter than the tails. Well, what ends up happening as n gets large, so as n approaches infinity, as n gets really large, so as the larger your sample, the T becomes the Z. So when I was in grad school, my professor basically just told me always use the T because it always works out. That's my opinion. I like that advice. However, the author of this textbook is not so much inclined to say that. So the key rule we need to know is this. If you know sigma, you use Z. If you don't know sigma, use S, therefore use the T. All right? And that is really the big difference here. Lastly, let's talk about what a confidence interval is. A confidence interval is not a probability. Right? A confidence interval is how confident you are that the true population parameter lies within a certain confidence interval. Right? So that is the key words when you're looking at your homeworks. Right? A confidence interval is a confidence interval percentage within some interval which contains the true population parameter. Remember, the two population parameters that we always look at are P and mu for our class. There is many out there. If you take more advanced statistics, you'll see that you can do a confidence interval on any population parameter, and there's hundreds out there. We will limit ourselves to P and mu, the mean and the proportion. But you can build a confidence interval on anything, because all a confidence interval is how confident you are, as the statistician, that within this interval that you calculated with your two critical values, plus or minus your margin of error there, that it contains your true population parameter. It is not a probability. It's just how confident you are that your interval contains the true population parameter. All right. This week, I really encourage you to start using technology, right? Because these confidence interval formulas are kind of tedious. It's fine to do one or two by hand just to get the understanding. If we go back a couple slides here, to do it by hand, you're doing all of this mess, right? But in reality, what I want you to take from these courses, from this course, and really understanding confidence intervals, is you're taking a point estimate, x bar p hat, and you're adding some margin of error to create some intervals. And then once you've created that interval, your interval is how confident you are that the true population parameter lies within that interval. That is the key takeaway for this week. All right. Excel can do some. I don't like their confidence interval formulas are pre-built in Excel. So if you're going to use Excel, I would type up the formulas by calling different cells. If you're comfortable with Excel, I encourage you to use it, especially if you use Excel a lot, so it'll just make you better with it. If not, or if you want to be, let me know and I can send you some, I can post some Excels. If technology is not your strong point, then I would highly encourage you to use StatCrunch. StatCrunch will do very well at building confidence intervals, so you just got to call the right one. And again, how do you know which right one? By what population parameter you're going with. I will post a video in Wednesday's announcement on showing you how I've done some of the homework problems using StatCrunch and how to input the data into StatCrunch. All right. Enjoy this week. Remember the e-text. I know I've gotten a lot of emails about that. It is more of an interactive, so I would highly encourage you to go through the sections. Start with the module overview. So click on week 3 module overview. Figure out what sections we're covering. It gives you a quick introduction in there, and then go to those sections and do your little workbook and interactive to get your notes. Get your discussion done by Thursday. And then start on the homework. Like I said, on Wednesday, there'll be another announcement showing more detailed information to assist with the homework. Please email me if you have any other questions, and I will continue to try to post at least 2 videos a week. Have a good week.